Hello and welcome back. We will now talk about constraints and collision objects, two very important subjects when creating destruction. So let's use the same file that we were using last time. I will dive into the geometry node for the bridge. The only difference now, you will notice that I created a column geometry and I am offsetting in space this column so it's floating above the bridge. So let me select the bridge. It is the same pre-fractured bridge and I will template the column. So it is quite high above the bridge and we will just let it fall and break part of the bridge. Now let's play the simulation without the column. I'm going back to my camera view and I'm going to play the animation. First of all, let's make sure that the RBD bullet solver is active. And now we can press play. So we know that the pieces from the center will fall. But what if we want to wait for the column to fall to break some of the pieces just where the column is impacting? So remember, we have been ignoring this second connection. And just as a reminder, the second output of the RBD material fracture contains this constraint. So let me lay down a null just to see this output. And these are the constraints that are being generated automatically by the RBD material fracture. And let's take a look what's happening here under the hood. I'll go to the geometry spreadsheet. And you will notice that we have a few points. And also, if you click here on the primitive segments, you'll notice that we have a few attributes for the primitives, a group. So these primitives are inheriting a group called concrete. And we have a rest length, a strength. And on the point side, we have a name. So this name is very important. Basically, each point of the constraints will have the name of the piece it is attached to. So again, this is done under the hood. We may get back to this when we're generating our setup from scratch, but just keep in mind that these attributes and of course the constraint geometry are being created here from the RBD materials fracture. Okay, so back to the solver. This time I will connect the second input. And now let's see the difference. What happens if I press play? So now none of the pieces will fall down because they are being connected with the constraint network. So let me press spacebar W to go into wireframe. And here you can see the network inside the geometry, which is holding the pieces together. So let's now talk about our collision object. I'm going to zoom in to the RBD bullet solver and take a look on the fourth input of the solver. You will notice there's a text, there's a hint that says collision geometry input 4. So what I'm going to do is to wire the column geometry into this fourth input. And let's just see what this does. I will press play. So remember, we have the constraints now on the bridge, so it will hold up. But the column is just floating there. And this is the default state of a collision object. So let's try this. I will replace the transform of the column. Just for now, I will move the column just above the bridge, or actually just under the bridge. Something like this. And again, let's press play and see what happens. Okay, it has the constraints. I will just temporarily disconnect the constraints for the bridge and press play. So notice how where this collision geometry is, the pieces will kind of stay. So they're colliding, they're hitting the column and then falling down. So the default state of a collider is something like an unyielding state where the collider won't move, but whatever crashes with it will react. But in this case, what we want is for the column to fall down. So I want it to be affected by the gravity and then crash onto the bridge. So I will connect again my constraints. And what I'm going to do, just to fix this, I'm going to lay down an RBD configure node and connect it just below my column geometry. And if we take a look at the properties for this node, remember we used in the last video this active attribute. So let's turn on the active attribute for the column and press play. So now the column is falling down and it's breaking part of the bridge. It's breaking a few of the constraints, and where these constraints are broken, the pieces will start falling down. So this is more what we wanted. Let me go to my camera view. I will also turn on the wireframe, so I'll press spacebar W just to see when the constraints are broken. And there you go, the pieces where these constraints are fractured will start to fall. So let's now take a closer look at the RBD configure node. So we activated now the column, and if you look a little bit down, if you scroll down on these properties, you will notice that we have a physical attributes that by default are configured as concrete. So this density, it's usually off, and the object will be treated as a concrete. So the mass, the bounciness, the friction are all set with these presets. So say if I want a heavier object, I can change this to metal. Or probably I have a wooden object, so I can select this wood preset. But you can also manually change this attribute. So let's turn on the density attribute and click here on the user density to override the original value that was set from this preset. Let's, for example, change the density to 5,000. This would make a much heavier column, and this will affect much more the concrete from the bridge. So notice how the braking is much stronger. We can even increase this to 10,000. And now the column will be extremely heavy and just break through the entire bridge. Or we can do the opposite. We may go much lower, say to 500. And this time the impact from the column on the bridge would be much smaller. Of course, you could also change the bounciness or the friction. You can turn this on. Click here in user and change these values to whatever you see fit. So the RBD configure node is very important to determine the final look of the simulation. So I will revert back to the very heavy column to 5,000. Just for you to know, concrete would have a density more or less of 2,500. So 5,000 is still much heavier than concrete. And for now, let's leave it like this. Now, another very important attribute that you can change here, and if you scroll upward, you'll notice that the attributes are being inherited from the object. These two attributes will come through if there's any velocity or torque assigned here, and they will be applied to the simulation. For example, let's add a point velocity just below the transform. So this node will let you add a velocity attribute. So let's take a look at the spreadsheet. Here on the transform, I only have the position attribute for the points. After the point velocity, you can add, for example, click here and add velocity, and add a directional velocity, for example, -50. And this is adding a velocity of -50 meters per second. So now the column will move very fast downward, and it will crash even harder onto the bridge. So let's take a look. I will click on my RBD bullet solver and press play. So now the column is coming in very fast and breaking the bridge. Let's now take a closer look at the constraints attribute. So for now, I have turned off this point velocity. I'm just letting the column fall down with the force of gravity. And to change the constraints attributes, you need to go to the RBD material fracture node. So remember, the constraints are being generated by this node. So here under the Constraints tab, you will find its attributes. So first of all, take a look at the name of the constraints. You may want several constraints in your workflow, and the name would be important to give each one of them different attributes. So for now, let's just leave it like this. And now take a look at the primary strength. So for my taste, the primary strength is way too high. Let's bring this down to, say, 1000. And let's take a look at the simulation. So now the constraints are breaking much easier. But we could even go lower than that. Let's try with 100. And you will immediately notice the difference. So now the entire bridge is breaking down. Of course, if you go the other way, the constraints would never break. Okay, so another important attribute is the strength variance. So let me go back to 100. I will select the null that we created just to check the constraints by themselves, and go to the geometry spreadsheet. So make sure you have the null selected, and here under the primitives attribute, you will find the strength. And notice how, although we have a strength of 100 here, none of the pieces have the exact 100 value. Some are higher and some are lower. And this is determined with this variance value. So if we bring the variance to 0, now all of the pieces will have the exact same strength of 100, which normally won't be very natural. So normally you will want to bring this variance value above 0. So let's go with 0.5. Another thing that you can do is you can switch the type of constraint once it breaks to a soft constraint. But this we will look in the next video.